Now next topic, that is energy stored in a capacitor. See here, suppose we have a parallel plate capacitor and we want to deposit charge Q on the capacitor. Now initially these two plates are neutral one. There is no charge on each plate. Now if we want to deposit Q amount of charge on the capacitor, it implies that on positive plate we have to deposit plus Q charge, and on negative plate we have to deposit minus Q charge. So for that, what we can do? We can transfer charge Q from plate number 2 to plate number 1. So if plus Q charge is transferred from plate number 2 to plate number 1, then on plate number 2 minus Q charge will be free. So in this way we can deposit the charge Q here. Now here, to transfer charge Q from plate number 2 to plate number 1, some external work that should be done. Okay, so here we have to do some external work to transfer the charge. So here what we have to do? We can transfer the charge with small amount. Suppose first we transfer the charge delta Q, then again delta Q, then again delta Q, then again delta Q, and in this way we can deposit the total amount of charge Q. Now suppose here we take some intermediate position for which charge on the capacitor, that is Q dash, means on positive plate the charge is Q dash on plate number 1, and the negative plate, plate number 2, the charge is minus Q dash. Clear? Now here in this situation, if we transfer some delta Q dash amount of charge from plate number 2 to plate number 1, then here we have to do some work against the field in this particular capacitor. Here suppose the potential difference between these two plates, that is V dash, and C, that is the capacitance of the capacitor. So we can write the potential difference here at this particular stage, that is Q dash by C, and work done to transfer the charge delta Q dash from plate number 2 to plate number 1, that is, we know delta Q into V dash. So delta W, that is delta Q dash into V dash. But V dash, that is Q dash by C into delta Q dash. So in this way, starting from 0 to total charge Q is deposited on the capacitor, or in other words we can say from 0 to charge Q is transferred from plate number 2 to plate number 1. So in this process, the total work done that we can calculate by integrating this equation. So the total work done to deposit charge Q in capacitor, W, that is equal to integration 0 to Q, Q dash by C delta Q dash. So here integration Q dash delta Q dash, C that is constant, so take it outside the integration. So we can write integration of Q dash, that is Q dash square by 2. So we can write 1 upon C into Q dash square by 2. First substitute upper limit. So we can write Q square by 2C, then lower limit, so minus 0. So total work done, that is equal to Q square by 2C. We can write this total work done in different ways. W, that is Q square by 2C. Now Q equal to CV. So here if we substitute CV, then it is C square, V square, 1 C cancelled. So we can write half CV square. Clear? Now here Q by C, that is V. So we can replace Q by C as V. So we can write half Q V. Clear? But here, see, the electrostatic force against which we have to do some external work. That force is conservative force. So this total work done, that will be stored in capacitor in the form of energy. So we can say the potential energy stored U, that is equal to Q square by 2C, or you can write the same thing as half CV square, and that is equal to half QV. Now let's calculate energy density in a capacitor. Energy density means what? Energy density means energy stored per unit volume of the capacitor. Now see here, we have a parallel plate capacitor for which, suppose the area of the plates, that is A, and the separation between two plates, that is equal to D. So volume of the capacitor, that will be A into D. Now see here, we have the equation energy U, that is equal to Q square by 2C. Now sigma, that is Q by A. So Q, that is equal to A into sigma. So Q is replaced by A into sigma. So here we can write A sigma whole square upon 2, and now C, that is replaced by epsilon 0 A by D. Capacitance of a parallel plate capacitor, that is epsilon 0 A by D, that we derived earlier. Okay. Now see here, this will be A square. This is A. So 1A will be cancelled. So we can write U, that is equal to sigma square A upon 2 into D upon epsilon 0. Now here multiply and divide by epsilon 0. So we can write here U, that is equal to sigma square by 2 A into D into epsilon 0 upon epsilon 0 square. But here we know this thing, the electric field between two plates of the capacitor E, that is equal to sigma upon epsilon 0. So this sigma square upon epsilon 0 square, that we can replace by E square. Okay, so we can write here now U equal to half epsilon 0, here one epsilon 0 is there, sigma square upon epsilon 0 square is replaced by E square into AD. But A into D, that is volume of the capacitor. So if we take this volume of the capacitor on left hand side, so total energy stored in the capacitor divided by its total volume, that will give you energy density in the capacitor. Clear? So here energy density of electric field in the capacitor, that is rho U equal to half epsilon 0 E square. So see here, half is constant, E0, epsilon 0 is constant, and into E square. So we can say this thing, in capacitor energy is stored in the form of electric field. Clear to all of you?